Okay, now that we have all of the machinery that we need set up for doing all kinds of integrals involving vector fields in 3D space, let's take a look at the big picture to figure out what the relationships between these different integrals might be. And we're going to start just by looking at reminding ourselves what the situation was in 2D. So in 2 dimensions, we have scalar functions, scalar valued functions, and if we take the gradient of a scalar function, we get a vector valued function, that is a vector field. And if we take the curl of a vector field in 2D, we get a scalar function again, right? In 2D, curl gives you, curl of a vector field just gives you a scalar valued function. And the integrals involving these things are related if you sort of integrate over the right sort of geometric objects. So if you integrate, so you can integrate scalar valued functions over points. We don't usually think of integrating over points, but what I mean here is, right, if you, right, we write this sort of thing all of the time, right, where you say go from x equals 0 to x equals 1. This is really integrating over 2 points, right? Because each point has an orientation. The first x value has a positive orientation, which is why there's a plus in front of it. And the second value has a negative orientation, which is why it has a minus sign. So when we plug in endpoints like this is really sort of a zero-dimensional version of integration. Right? The zero-dimensional version of integration is just evaluating a function at a point. So, so we can do zero-dimensional integrals of scalar-valued functions over points. We can do integrals of vector fields over curves. And these two are related by the fundamental theorem of line integrals. Right? The fundamental theorem of line integrals says that, essentially it says that if you have a curve, the integral over the curve of the gradient of a function, d dot dr, which is that one, is equal to, we don't usually write it this way, but it's the integral over the boundary of the curve of the function itself. Right? And that's, this is this one. Right? Usually we write this as plugging in the endpoints and subtracting. Okay, so the fundamental theorem of line integrals gives us a link between these 2 steps in this sequence. We can also integrate scalar functions over regions, and there's a relationship between these 2. This is Green's theorem. Right? Green's theorem says that the integral around the boundary of a region of f dot dr is equal to the double integral over the interior of the region. Oh, this is an integral around a closed curve, of course. Integral over the interior region of the curl of the vector field dA. Right? Also, another important feature of this diagram is if you take 2 steps along this chain, you always get 0. For this particular diagram, there's only one place you can start where there are 2 steps available, and that's here. Right? So if you start with the scalar function, and you take the gradient of it, and then you take the curl of that, you have checked that this always gives you 0. Okay, so let's look at the corresponding situation in 3 dimensions. So here's the corresponding situation in 3 dimensions, right? We have scalar valued functions that we can still integrate over points, which again just means evaluating them. If you take the gradient of a scalar valued function, you get a vector valued function. Vector valued functions you can integrate over curves, which are, right, so points are 0-dimensional objects, curves are 1-dimensional objects. If you take the curl of a vector field in 3D, you get another vector field. And we can integrate vector fields over surfaces. Surfaces are 2D objects, of course. If you take the divergence of a vector field, you get a scalar valued function again, and we can integrate scalar valued functions over volumes. Volumes are, of course, three-dimensional objects in 3D. Also, if you take 2 steps, if you start anywhere on this diagram that has 2 steps available, and you do 2 steps, you get 0. So I have had you check in homework, I think, that if you start here and take 2 steps, you get 0. So that means that the curl of a gradient of a function is always 0, just like in the 2D case that we talked about a second ago. But also, if you start with a vector field and you do curl and then the divergence of that, you always get 0. Okay. So with this setup, of course, it seems like, well, there ought to be some links between integrals in these different locations, just like there was in the 2-dimensional case. And actually, we already have one of the links. We still have the fundamental theorem of line integrals, that says that the integral over the boundary of a curve of a function, that is, evaluating the function at the endpoints and subtracting, is equal to the integral over the curve of the gradient of the function, d dot dr. Right? This is the fundamental theorem of line integrals. This is as true in 3 dimensions as it is in 2 dimensions, with exactly the same proof, by the way. The proof that we use to prove this in 2 dimensions works just as well in 3 dimensions. So it seems like, you know, if there's any mathematical justice in the world, there should be theorems that relate integrals in these 2 spots. So what we're going to do now is attack one of these 2 spots. We're going to attack this one. So we're going to think about what sort of integral of vector fields over curves might be equal to what sort of integral of vector fields over surfaces. And it might take a little experimenting to hit on the right idea, but the idea is to measure flow, because we have 2 ways we can measure flow. If we have a surface like this that's orientable, and we ask about the flow of some vector field, around the boundary of this surface, there's 2 ways we could think about this. First, we could concentrate just on the boundary, right, which is the bottom rim of this surface that I've drawn. So to measure the flow, we might integrate around the boundary, and the boundary is a closed curve, so I'll put my little ring on my integral there. We might just calculate the flow directly on the boundary by doing a line integral around the boundary. Okay, but there's another sort of more global way using the entire surface to measure the flow, which is if you sort of zoom in on a little patch of this surface, right, there's a little, if this vector field is circulating around this little patch, that's like a little bit of flow around the boundary, right? So if we could integrate what the circulation is doing at each little patch on this whole surface, that might be another way to measure the flow around the boundary, because, you know, for patches on the interior of the surface, they have neighbors also with their own little circulation, and on adjacent boundaries, of course, these are the same boundary traversed in opposite directions, and so the circulations should cancel, right? So the idea here is to integrate over the surface, right, d sigma, something that should measure the circulation. Well, how do you measure how a vector field is rotating? You take its curl. So maybe what we should integrate is the curl of f. And of course, we need a normal vector. We need to orient our surface to make sense of this integral. So we have sort of a local way near the boundary of measuring flow around the boundary, and we have kind of a global way looking at the entire surface. And it feels like these should be related, right? This is kind of similar to what happened in terms of what happened in Green's theorem. It is different because, right, this is not just a double integral over a region in a plane. It's actually it's an integral over a surface, so it's more complicated. But it seems like a similar idea. Well, in fact, Green's theorem is just a special case of this idea, because a plane, right, we can imagine, Green's theorem is in 2D, but we can imagine that that our 2D vector field and our 2D surface in the xy plane is actually embedded in 3 space, right? So we were kind of hoping that the line integral around the boundary is equal to the double integral, or the integral over the surface of the curl. But if we write out both of these in the special case where our region is in the xy plane, so I've called it S, but right, this is really a region in the xy plane that looks like a bunch of points that are x, y, 0. And if our vector field has no z component, so it's really a 2-dimensional vector field, but somehow sitting in 3-dimensional space, then the integral around the boundary of our surface is, well, it's the integral, right, in the xy plane, it's the integral around, it's the usual line integral. The double integral over the surface is dot n d sigma. Well, this double integral simplifies a lot in this special situation. So the surface is really just a region in the xy plane. The curl of this vector field, well, we can just calculate the curl of this vector field. It turns out it's 0, 0, partial n partial x minus partial m partial y, which, you know, looks like the 2D curl, but we're dotting with n. But because this region is in the xy plane, we can just choose an appropriate normal vector. Because the region is in the xy plane, the unit vector in the z direction will serve as a normal vector for this region. And then d sigma, well, again, because this region is confined to the xy plane, d sigma is just the same thing as dA in the xy plane. So this dA is in xy plane. Okay. So you can see that when you work out this dot product, what you end up with is the double integral over the region of partial n partial x minus partial m partial y dA. And right, Green's theorem does say that these two things are equal. So this is just Green's theorem. So Green's theorem is a special case of what we guessed to be true. So this is confidence building that maybe our guess is actually correct. Although this does introduce a subtlety that maybe we hadn't noticed before, which is to make Green's theorem true, we have to have our orientation correct. Okay, we have to orient the boundary of the region in Green's theorem so that the region is on the left as you go around the boundary. But things are more complicated in 3 dimensions because, right, what does on the left mean if your boundary sort of wanders around in 3D space, right? As you traverse the boundary, there's no single notion of what left means. So instead, we have to come up with a more complicated relationship between the orientation of the surface and the orientation of the boundary. Okay, and you know, there are 2 ways to orient the surface, there are 2 ways to orient the boundary, and so you can just experiment to see which way gives you the same thing, and which way gives you opposite things, right? Choosing the wrong orientations will give you a minus sign when you shouldn't get a minus sign. So rather than doing that experimentation, I'll just tell you what is the correct way. And the correct way to orient the boundary is this. Right, the boundary has some orientation. The surface has an orientation. And also, as we traverse the boundary, we still want the surface on our left. Okay, and so I've tried to draw these as if they're at right angles to each other. And so we have this kind of setup with the orientation of the boundary, the orientation of the surface, and then this arrow is supposed to depict that the surface is on the left. Okay, well, if you look at this, this is a kind of like a right-handed coordinate system, and so what we can use to make sure that we get the right boundary is yet another right-hand rule. Okay, the right-hand rule for orientations of surfaces and their boundaries looks like this. So the orientation of the surface is your thumb, the orientation of the boundary is your index finger, and your middle finger must point into the surface. So if we look back at this diagram, this is oriented correctly because, right, if I put my index finger pointing in this direction, sort of rightwards and inwards a little bit, and I put my thumb in this direction, upwards, my middle finger will be pointing into the surface. If I have things oriented the wrong way, so if the orientation for the boundary is going that way and the orientation for the surface is going this way, right? Now if I do the right hand rule with my index finger pointed this way and my thumb pointed that way, my middle finger is actually coming out of the screen instead of going into the screen, right? The surface is into the screen at this point. So this is oriented incorrectly using this right hand rule. So that's how we'll choose compatible orientations. And the key thing about this is that you can use the orientation for the surface to decide on the orientation for the boundary, or the orientation for the boundary to decide on the orientation for the surface. So it goes both ways. So let's just look at an example of how an orientation on the boundary induces an orientation on the surface. So let's suppose that this is our surface. So our surface is going to be this paraboloid, like this. Okay, let's choose. Let's say that the boundary, which is this rim on the right-hand end, is oriented this way. So that means at this point at the back, the orientation for the surface is going up like this. I'm sorry, the orientation for the boundary is going up. And going this way around the boundary, at this point, the surface is to this side. Okay, so now we want our index finger pointed this way and our middle finger pointed this way. When you do that, our thumb is pointing out. So thumb is pointing out, right? When we get around to this point, well, now the boundary orientation is going this way. That's our index finger. The surface is still to this side, to the left, so that's our middle finger. And so now, at this point, the thumb is going to be pointing in, right? So if I draw some surface orientation vectors, right, they're going to go outwards, downwards, inwards, upwards. At this point, it's going to be going rightwards. Okay, so the orientation so given this orientation on the boundary, the induced orientation on the surface is rightwards and inwards. Okay, so let's look at an example of how this goes the other way. Let's use an orientation on a surface to induce an orientation on the boundary. This time for our surface, let's take, how about a cylinder that looks like this? Okay, and for the orientation on the cylinder, let's take the orientation that goes out like this. Okay, so this time, first of all, notice the boundary is in two pieces. There's a piece of the boundary that is this upper rim of the cylinder, and there's a piece of the boundary that is this lower rim of the cylinder. So we'll need to, the orientation on the surface induces an orientation on both parts of the boundary. So we'll need to work out both of those orientations. Okay, so at this point on the boundary, the surface orientation is, right, this surface orientation is going outwards. So the surface orientation is going mostly into the screen and a little bit back like this. Okay, so this is, it's hard to sort of, looking at it, it's hard for me to make my mind believe that this vector is going mostly into the screen, but keep in mind that this is our surface orientation. It's mostly going into the screen. Okay, at this, and that's our index finger. I'm sorry, that's our thumb. Yes. Okay, at this point, the surface itself is to the lower left. Okay, and this is going to be our middle finger. So surface is on the left. And then if I try to orient my hand to make that happen, I have to go like this. So I have to make my index finger point this way. So index goes this way, and this is the orientation for the boundary. Okay, so this orients this part of the boundary this way. So this way. Right? Maybe just as a double check, we can check that this is the correct orientation at this point. So the surface normal is coming out. Maybe it's a little easier to draw it over here. Surface normal is coming this direction. The surface is to this direction, and so with my thumb going in the going out and my middle finger going down and to the left, my index finger does indeed have to point this direction around this part of the boundary. So that checks out. So now let's do this bottom part, and I'll be smart this time and pick this point. So the surface normal is going to go that way. That's our thumb. This time the surface is in this direction, so that's our middle finger. And to make this happen, I have to go this way. My index finger ends up pointing this way around the boundary. So I am going this way. Okay. No, I've got that backwards. Sorry. Yes, I've got that backwards. My index finger has to go this way. So this is going this way around the boundary. Good, that's what I expected. Okay, so the idea here is if you have an orientation on the surface or on the boundary, it induces an orientation on the other one, right? So there's only one way to choose a compatible orientation, and we're always going to use this right-hand rule. So with that caveat, now we have a complete guess for what we think might be true for this relationship between a line integral and a surface integral of the curl of the vector field. So we think that maybe the line integral around the boundary of the vector field is equal to the surface integral over the surface of the curl of the vector field if we have compatible orientations. Of course, if you don't have compatible orientations, one of these will be the negative of the other one. So I guess our next job is to figure out how are we going to prove this.